Okay, so the last speaker of today's session is Viktor Jahnke from GIST, and he will tell us about some recent work on holographic teleportation and conservation loss, diffusion on traversable wormholes. So please, Viktor, the floor is yours.
Well, thank you very much for the introduction, Hugo. So it's a pleasure to participate on this workshop. So let me first thank the organizers for this opportunity. So as Hugo said, I'm going to be talking about traversable wormholes and conservation laws. So this is based on my recent work in collaboration with Youngjung An, Sang-On Bak, and Kyung-Young Kim. So let's get started. So, recently, Gao, Jeffries, and Wall realized that wormholes in ADS can be made traversable by coupling the two asymptotic boundaries. And from the perspective of the boundary theory, the traversability of wormholes in ADS can be thought of as a teleportation protocol. Okay, so this is interesting because it opens the possibility to study some setups which people call, and I quote, quantum gravity in the lab. And however, the effects of conservation laws on traversable wormholes have not been explored yet. So in this work, we study T+1 dimensional wormholes that are made traversable by coupling the two asymptotic boundaries with U1 conserved currents. Okay, so our motivation to do that is as follows. The traversability of wormholes is typically connected to their scrambling properties. And the scrambling properties of black holes change under the presence of conservation laws. For example, OTOCs, they display a power law behavior with time if they involve conserved current operators. So this suggests that conservation laws affect the traversability of wormholes. And for example, the wormhole opening can in principle depend on transport properties of the black hole horizon. Okay, so let me explain the physical setup that we are going to be studying. So I'm going to consider asymptotically ADS two-sided black holes. Above here, I have a Penrose diagram of the black hole, and which I am going to be considering, and the metric is shown here. So let me see if I can use a pointer here. Okay, no, this is not a pointer. Sorry.
I can see your mouse.
You can see my mouse. Okay.
Yeah.
Okay, so basically, in the right exterior region here in this geometry is described by CFT on the right boundary, and the same goes for the left CFT. And so the full geometry is described by a thermal field double state, which is constructed by entangling the two CFTs. Okay, so if I consider a constant time slice here in the geometry, this geometry has the shape of a wormhole, and this wormhole is not traversable. And let me now explain why. Okay, go back to mouse. Okay, so the reason for the non-traversability of wormholes is basically the average no energy condition. And the average no energy condition basically states that the integral of the stress energy tensor along no geodesics is positive. So this basically tells you that the energy of your matter fields is positive. So if you have here like a two-sided black hole, and if you want to send a signal, which is shown here in blue, from the left to the right side of the geometry, your signal just hits the singularity and never makes it to the right boundary. So maybe to make the signal to cross to the other side of the geometry, you can send some matter fields to interact with the signal, and hopefully the matter fields will change the trajectory of the signal in such a way that the signal will reach the right boundary. However, one can see that one can compute how much this trajectory is changed by the matter field. Here for simplicity, I'm just considering a matter field which is modeled by a shockwave type geometry. And in this case, the change in the trajectory of the signal can be computed very easily if one considers like a no signal. And this change in trajectory is basically given by an integral of this metric fluctuation, HVV, along the v direction. And if one then uses the Einstein's equation of motion, one can see that this integral is proportional to the integral of the stress energy tensor along this no geodesic. So one basically see, and the average no energy condition implies that this quantity is positive. So we see here that delta U is positive, and the interaction with this matter field only makes the situation worse. The signal never makes it to the right boundary. And from this analysis, we can see that to have a traversable wormhole, I would need some matter field with negative energy, in such a way that delta U would be negative. However, classically, the reasonable classical theories, they satisfy the null energy condition, which is basically states that the integrand here in this inequality is positive. So the null energy condition implies that the average no energy condition, and basically prevents the existence of wormholes at the classical level. So to create a traversable wormhole, we need to consider quantum mechanical effects. Okay, so let me now explain Gao, Jeffries, and Wall construction of a traversable wormhole. So what Gao, Jeffries, and Wall did, well, they basically work in the context of the semi-classical approximation. So they write Einstein's equation as shown here, and they treat.
Okay, go on.
Okay, so Gao, Jeffries, and Wall, they treat the gravitational fields classically, but the matter fields are treated quantum mechanically. So they basically consider Einstein's equation and replace the right-hand side by the quantum expectation value of the stress energy tensor of the matter fields. So what they do to make the wormhole traversable, they just introduce a coupling between the left and the right boundary. And physically, what happens is that this introduces, that they consider a scalar operator. So this introduces some scalar field in the bulk. And because this scalar field has this particular boundary conditions, one can choose the deformation in such a way that this scalar field in the bulk has negative energy, which makes the wormhole traversable. So yeah, so basically what they do is to introduce a double trace deformation, which introduces a negative energy in the bulk. So it might be a bit weird to think about a field with negative energy, but this is somewhat analogous to the Casimir effect. So in the Casimir effect, you have two conducting plates, and the vacuum energy between the plates is smaller than the vacuum energy in the region outside of the plates. So actually here, like if you compute the vacuum energy, you get some infinite results, both inside and outside of the plates. But only after renormalizing this result, let's say if you renormalize the result and say the energy in the outside region is 0, then you end up with something that it's negative. But the only thing that's happening here is that the energy for this scalar field is just slightly below the vacuum energy of the same system without the perturbation. So this is somewhat analogous to the Casimir effect. Okay, so let me show you the results that the Gao, Jeffries, and Wall obtained. They computed the so-called average no energy, and they have a analytic formula for it. And it depends basically on two parameters: the scaling dimension of the scalar field that they use to open the wormhole, and it depends also on the time t0, which is basically the time at which you introduce the deformation. So this result is somewhat complicated, but if one, and it's derived for a perturbation, like they include the perturbation at time t0, and the perturbation remains in the system forever. You can get a somewhat simpler formula if you consider like a delta function as the source of this perturbation. This was derived by Frey-Vogel, and you get this result. And the important thing about this result is that at large times, the average no energy has this exponential behavior as a function of the time t0. I am going to use this to compare with my results, like for conserved current operators. Okay, so this is a summary of Gauss-Jeffreys and Wall result. So now our setup, like we are going to open the wormhole considering conserved currents. So basically, we are just going to replace the scalar operators by conserved current operators. And for simplicity, we consider just the time component of some conserved currents. So we consider a deformation like this, and like the story is as before, but the difference now is that since I'm considering conserved current, this introduces some in the dual picture. This introduces some gauge field in the bulk, and this gauge field will be the guy that has negative energy in our setup. So this is interesting because this gauge field has some diffusive behavior which will affect the traversability properties of the wormhole. Okay, so let me now try to explain.
Excuse me?
Oh, yes, sure.
So if I'm reading correctly, your figure shows that the signal coming
Yes.
from side left minus, I mean the red, your red line
Yes.
is crossing the boundary, right? Sorry, horizon.
Yes.
So how can it be possible?
So you mean like how it's possible that the signal crosses the horizon and then leaves?
Yeah. It is coming out of the horizon, right?
Yeah, that's true. That's true. And it leaves because it interacts with this negative energy in this interior region. So basically,
And,
yeah.
So what that means actually? You are saying some I mean the analogy with the what the
okay, so
confine the system, but
yeah, so basically the interaction between these two particles, like if I model this negative energy with a shock wave, usually when you compute a geodesics crossing a shock wave,
is it what you are suggesting or what they are suggesting?
I know, I mean, like this is like what it's also the case in their setup, like basically this negative energy, which is shown in blue, it has the effect of it changes the trajectory of the signal by just a no shift in the U direction. But normally this shift is positive, and it's called time delay, Shapiro time delay, which is a well-known effect of this geodesics. Right. So, but like the thing is, this quantity is always positive. Like average no energy implies that this quantity is positive. And what Gauss, Jeffreys, and Wall observed is that this delta U can be negative if one consider quantum mechanical effects. So physically, it's like the particle is sort of like escaping from the black hole.
So is that something which is accepted in the community, or what's going on here?
No, I think so. I think this is accepted in the community.
Why it is accepted?
I mean, like it's just a quantum mechanical effect. Like at the classical level, nothing can escape from the black hole. But
I mean, do you mean by quantum mechanical something which is offshore?
Okay, so yeah, so it's just like it's not really quantum gravity. It's just like semi-classical. So basically, only the matter fields are treated quantum mechanically, but the background is not quantum mechanical.
Comment on it?
Yeah, actually, I have some comment because we Hangjin and I discussed before after lunch, and this is what you mentioned. This is coupling between shifted left and shifted right.
Yeah,
so
yeah.
That makes it possible. So.
Oh, yeah. That's true. Yeah. So I mean, like, if you think about in the context of Hongliu's lecture, like, it's not really. I mean, like, how is it possible that you somehow describing a phenomenon in the interior region, right? So, and this is possible because you have a direct coupling between left and right side of the geometry. I mean, like, I think this is sort of consistent with to what Hongliu said, like, to describe the interior region, like, you need some sort of coupling between the two boundary theories.
I see. So this is what you call it, reversible, you say?
Yeah, that's true. Okay. Yeah. So in our case, it's basically the same story, but with conserved currents. So let me try to walk you through this calculation. So basically, yeah, what we want to compute here is the stress energy tensor, the expectation value of the stress energy tensor. But we need to consider the quantum mechanical effect of this deformation, which is shown here in blue. So we start with the stress energy tensor for the gauge field, and we consider unperturbed metric like this. And we are basically we want to compute the VV component of this stress energy tensor. So for simplicity, we consider the spatial components as 0, and we find that the stress energy tensor, like at the classical level, is given by this formula. So if I want to compute the quantum expectation value, I could just take a expectation value on both sides of this equation. But on the right-hand side, I would end up with some divergence because I have the same field computed, the two fields computed at the same point. So you need to somehow regularize this. And the method we used here is this so-called point splitting method, in which you basically compute each field in a separate point. And so basically this expectation value of the stress energy tensor can be computed from a 2-point function after a proper regularization.
Hi.
Yes.
Excuse me.
Sure.
Because this is, I guess, maybe last session, so maybe you can have more time. So let me just ask you.
Yeah.
Can you say a little bit more specific about the detail? What is the role of that decoupling term? Which makes possible that this, I mean, the negative energy shift can be happen. So what is the critical role of this coupling term? The previous page.
Yeah, so sure. I think like I'm gonna try to explain this in the next slides. So okay. Maybe it will be more clear, but if it's not clear, please
go
me
on
again. Yeah. So basically the stress energy tensor is computed from this 2-point function. However, I have to compute this 2-point function, but under the presence of the deformation. And okay, so what we do, like we have this 2-point function, which is initially written in terms of Heisenberg operators. And by introducing the coupling, we basically here in the second line, I'm writing the same 2-point function in terms of operators in the interaction picture. And the evolution operator here involves the left and the right, the currents acting on the left and on the right side of the geometry. So basically here, you can see that this 2-point function, the interaction piece couples the two sides of the geometry. So we can do this calculation at first order in perturbation theory. So we basically expand this evolution operator to first order. And the parameter h here is basically the parameter that couples the two sides of the geometry. And okay, so So G has this expansion, and the stress energy tensor has a similar expansion. So one can show, like, and Gao, Jeffries, and Wall show in their paper, that the zero order contribution here to the stress energy tensor does not contribute to the wormhole opening. So that the integral of this TVV along the V direction just gives you 0. And this is good because the G0 contribution is also it's piece of this 2-point function that needs to be regularized. But like, we don't need to care about this because we know in general that this gives no contribution to the wormhole opening, which is consistent with the fact that if you turn off the perturbation, like, this should be non-traversable. So the first order contribution can be non-zero. And in fact, for the perturbation that we consider here, ANEC is violated if H is smaller than 0. So basically, if you expand this time evolution operator, you find that this first order contribution to the 2-point function, it's given by an integral which involves operators, bulk operators, AV, and boundary operators, J left. And using large N factorization, you can see that this G will be given by some integral involving products of bulk boundary propagators. So those these bulk boundary propagators will be the essential ingredient to compute G. And basically you can see, like, they involve a bulk field and operators on different sides of the geometry. So here I already wrote a guy on the left side as a guy on the right side using some identities. So what we see is that, like, basically to compute these propagators, I first compute a bulk-to-bulk propagator involving only bulk fields. And then taking one of these guys to either to the left or to the right boundary, we can derive the propagators above. And I guess, so trying to answer your question, like, if these operators were on the same side of the geometry, this formula would not apply, and I think somehow I should be able to see that this should be 0 if both of these guys are on the right side of the. Let's say if I put this guy on the right side of the geometry, and I take a step back, I should be able to see that this would lead to. I mean, like, if you only act on one side of the geometry, it's impossible to open the wormhole. But I think I'm not, like, really in position to show this here. But this is discuss it with some more detail in Gao, Jeffries, and Wall paper. So I hope I'm not sure if that's a satisfactory answer, but so let me move on here. Okay, so the essential ingredient is the computation of bulk-to-bulk propagator. Okay, so we consider a ADS Schwarzschild black hole, and, like, if I consider, since I'm deforming the theory with the conserved currents, I have the corresponding bulk field excitation is a gauge field. So if you solve the equations of motion for a gauge field, like, it's in general hard to solve this equation of motion, but one can solve this equation in the hydrodynamic limit. And the behavior of the gauge field is essentially controlled by a diffusion constant. So the parameter that will be relevant for us is this uppercase D here, the diffusion constant. And this diffusive behavior basically tells you that the gauge field spreads over a large region of space-time points. Okay, so to compute the propagator, we actually need to solve these equations with the source. and we get these results. So once we have the GTT propagator, I can obtain the bulk boundary propagator, then I compute the two-point function, then I compute the stress energy tensor, and finally I compute the average no energy condition. So by doing all these steps, we can show that for a perturbation sourced by like a delta source, we get this result shown here. So there are a few features of this result that I would like to discuss. First of all, like as before, like we have some exponential suppression at large times, but we also see some power law behavior with time, which also appears in correlation functions involving conserved current operators. Like this is normal in like two-point functions. And this also appears in OTOCs involving conserved current operators. And this also is the case here. So one interesting feature of this result is that the diffusion constant appears here in the denominator. So this sort of suggests that diffusion makes it harder to open the wormhole. And on the other hand, if I could somehow tune the value of D to be very small, it seems like the wormhole opening can be arbitrarily large. Okay, so the physical picture for this dependence on the diffusion constant is as follows. So basically, because I'm here showing this is the left boundary, this is the right boundary. Here I'm using a Kruskal diagram. So basically, the gauge field that I introduce in the book is delocalized. So the interaction of this gauge field with the signal that makes it possible to cross to the other side of the geometry. However, this interaction is sort of weak because the gauge field it's kind of mirrored over large region of space-time. So because of this delocalized nature of the gauge field, the interaction is weaker, and this makes it harder to cross to the other side of the geometry. So that's the physical picture for what's going on here. Yeah, so okay, so this delta U, this wormhole opening also, so it basically allows us to send a signal from the left side of the geometry to the right side. But there is a bound on the amount of information you can transfer. And the reason is as follows, like the back reaction of the signal tends to decrease the wormhole opening. So if I send just one particle, the particle crosses to the other side and everything is okay. But if I try to send too many particles, then the back reaction of these particles might be very large, and this tends to close the wormhole. So that, together with the uncertainty principle, implies a bound on the amount of information that can be transferred through the wormhole. So let me try to explain this with some more detail. So like consider a signal with any bits, so any particles, each particle with momentum p each. So the total momentum of the signal, it's any bits times the momentum of each particle. So we don't want that this total momentum to be we don't want this total momentum to be very large because the back reaction closes the wormhole. So we want to be in the probe approximation. But if I send too many particles, maybe I'm going to be outside of the probe approximation. However, naively, you can say, okay, maybe if I send many particles with very low momentum, I can send as many particles as I want. But that's not true because of the uncertainty principle. Like if the momentum of the particle is very slow, then the corresponding wave function will occupy a very large region in the U coordinate. But this particle, maybe this delta U will be so large that the particle will not fit in the wormhole. So if you require that each particle wave function should roughly fit the wormhole, you can come up with the bound on the amount of information you can transfer through the wormhole. So using the probe approximation and the result for the wormhole opening, Maldacena and collaborators found that the number of bits that you can send through the wormhole is upper bounded by h. H here is the parameter controlling the coupling between the two boundaries. So they derived this bound. This bound can also be derived in higher dimensional setups, and it's roughly the same story. It's not a very precise bound. It's just like a parametric bound. And this parametric bound can also be derived in our setup.
Excuse me?
Yeah, sure.
So n bits means that number of bits?
Yeah, that's the notation people use, but in this case, it's just like the number of particles I'm sending through the wormhole.
Right. So h in this case is a positive or negative?
I mean, like this is the absolute value of h. Sorry, here it's positive. And like.
And by the way, I mean, I still have the problem in the interaction term, h times or left or right, and then can you show me it again? I'm sorry.
Yeah, sure. You mean this h, for example, or you want to see the picture? So okay, so
no, that's fine. I mean, so
previously.
So you consider x and two operator, JT left and the JT right is occupying the same position x, right?
That's true. Yeah.
I mean, maybe left world is at Andromeda, and the right, I mean, the operator is leaving our universe, for example, the galaxy. And what do we mean by having the same position? So you just arbitrarily assign.
I mean, like, they could be on different positions.
Then it's not local action, right?
Yeah, no, I mean, like it's already non-local because the two asymptotic boundaries are very far apart.
Yeah, so this is a kind of a non-local action.
Yeah, that's true. That's true. It's this non-local interaction that it's kind of
because time at least is different. Huh?
Yeah. Time here, like time goes up on the right side and down the left side. But you're right. Like I could, in principle, put these guys at different positions, but like I would have some additional parameter.
So what you are basically saying is that such a introducing such a non-local, maybe interaction term can make the wormhole in the dual space open.
That's true.
Maybe
yeah, that's true.
That is your message.
Yeah. And like you could think about this in like you could think about some physical setup on the right side, some condensed matter system, and let's say you somehow consider an identical copy of the system, and you somehow entangle the two systems in a thermal field double state. Then that means if I apply the same operator on both systems at time 0, then a very early perturbation on the left side system should show up at very late times on the right side system. And that in principle is possible in like lattice systems or systems even in the laboratory. And people call this like either regenesis or many-body quantum teleportation. But that would be like the experimental realization of this type of setup, at least from the point of view of the boundary theory. So from the point of view of the boundary theory, I think it's well defined. The interesting thing is that,
Sorry, Viktor. I have a suggestion since we are discussing many aspects of the work. I would suggest maybe if you can wrap up the talk in maybe 2 minutes, and then we can move on to some more
sure
discussion.
No problem.
Okay, great. Thank you.
Yeah, so basically, what we find here is that the bound on the information transfer is also controlled by the diffusion constant. And you can see that if the diffusion constant can be very small, maybe the upper bound can be like huge. But in some systems, the diffusion constant there is like a lower bound for this diffusion constant. In our case, this is the diffusion constant is just some number, but like maybe in some more interesting setups like these condensed matter models, you can find you can replace the D also depends on some external parameters, some like time, yeah. So let me move on here. So basically, our conclusions is that it's possible to generalize Gauss-Jefferson wall traversable wormhole construction to the case where the double trace deformation involves conserved current operators, and the wormhole opening depends on the charge diffusion constant, and the same is true for the bound on information transfer, and I expect this to be true like in more general setups. Like if you consider another type of conserved current, maybe the wormhole opening will depend also on the corresponding transport property. So as some future directions, I would like to say that I think it would be interesting to consider other types of conserved currents and fields. And another interesting direction would be to understand how bounds on diffusion constants affect the information transfer. And also, I think it would be nice to study the effects of conservation laws in the context of many-body quantum teleportation. I think this has not been explored yet. So that's all I have to say. So thank you for your attention.
Thank you, Victor. Yeah, so I think it's good if we start with some questions.
So before we go back to the previous issue, I just want to ask one more question, which is
Sure.
about the conservation. I mean, the conservation.
Yeah.
By conservation, do you mean that some quantities are conserved in one boundary or in altogether boundary left and the right boundary together?
I know, yeah, I mean, like, just like, I'm just thinking about, for example, some gauge field disturbance on the geometry. So in our case, like, you have gauge fields on both sides of the geometry. But yeah, what I mean is just like some gauge field, but like I could have like some.
No, let me be more specific. So suppose you just send one information from left to right, right?
Yeah.
If it is not stuck in the bulk, then it's natural that the whole information is conserved in the whole world, right?
Yeah.
So the question is, what forbid the information is not in stock at the bulk, but it just goes through all the way of from Andromeda to our universe. Why it cannot be stock at the bulk? So what makes your thing in the be conserved?
Okay. So you're asking about the signal.
Yeah.
No, I mean, like here, like
signal charge doesn't matter actually. No. The information.
Yeah, but it's, I mean, like by conserved, I mean, like these currents they do satisfy some conservation law.
Because like that is a very dangerous statement, because you see that I don't think that can be correct. Because I can prove it, because if you can send something from left to right, it can be globally conserved, but not locally. But your equation, I mean, the conserved equation is a local conservation equation, which cannot be correct here.
Why not?
Because you just send the information from left to right.
You mean globally in the sense?
If you look at the left world, then that information is missing from the left, right?
But that statement is about the negative energy, not about the signal.
What?
No, the signal is not conserved. Like just the negative energy is conserved.
Reversibility. I guess that I thought that the things and the bits are just the same.
You mean like you're just thinking about some signal which is would be like some conserved current.
Signal means, for example, one charge is a traverse.
Okay.
I mean, the
Yeah, I mean,
from
globally
left
is
to
not,
right.
I mean, like you're saying globally is not, globally is conserved because it goes to the other side of the geometry.
Conserved, I mean, the globally conserved, but not locally. That's what I meant. It disappeared from the left world, and then it appears at the right world. That's what wormhole means, right?
Yeah.
So you just assume that there is a traversability, and then you still assume that local conservation law. I don't think that's the right attitude.
I understand your comment.
You understand or don't understand?
No, I understand. I understand
okay.
the concern. So you think the conservation is inconsistent with the traversability?
Right.
I mean, like I could consider the conservation at the classical level.
And is it this conservation in the safety point of view, or you are?
No, this is like in the bulk, yeah. But like also in the CFT also, yeah.
But it depends on the statistical model. So
Yeah, right. So if this is the bulk, then it's okay.
No, this is the bulk, yeah. This is the bulk, yeah. This is a conserved current in the
bulk. Oh, okay. So your conservation is at the bulk.
Yeah.
But bulk is I see. So maybe it's not something physical. But is there any implication about this to the boundary world?
That I don't know. So you mean like? So you're basically saying that from the boundary point of view, this cannot be true at the local level.
Exactly. That's what I mean.
I did not consider this issue, but like yeah, I use this condition in the book, not at the boundary.
Oh, okay,
that's
enough. Okay, thank you very much. So this is the bulk one, so I understand it.
Yeah.
And then let's come back to the previous issue.
Okay.
All right. So I forgot what was I talking about. But yeah, 8, the left-right connection. Okay.
Yeah, sure.
So I thought that if the purpose of this gluing left and right through this holography is just to consider the entanglement, right?
Yeah.
And then that through this adding left and right direct, I mean the operator, I mean this interaction term, I didn't expect that there is a so stringent restriction to the H or whatever, because it's a common sense that you see that whatever interaction there is, I mean, if you have those two sheets together,
I mean,
and then if you have an interaction between the, I mean, the one sheet to the other, then entanglement is automatic. So now I mean, here, like, why there is such a stringent in the construction, I mean, the restriction to this, this is a boundary interaction, right?
Yeah, that's true.
Right. So can you explain things, I mean, from the sign of H from the boundary point of view? Because you see, holography is just a tool. Bulk is a tool. So we must be able to understand the existence of the negative H from solely boundary point of view, right?
Yeah.
Is there any, I cannot think about any kind of a reason why there should be negativity in the just the perturbation term.
So you're basically complaining about the fact that this is traversable for some particular sign of H.
Yeah.
Okay.
So you see that whether you are looking at from the bulk point of view or boundary point of view, things should be just it's just if there is a holographic dual, then it's the same thing, right? Therefore,
yes.
And this interaction term is just a boundary term, right? So
yes.
why? I mean, in order to for the two sheets to communicate together, why one sign is possible and the other sign is not possible?
Oh yeah.
From boundary point of view.
From boundary point of view. So yeah. So okay. So I can answer this from the book point of view, because basically, let me first answer from the book point of view, then I'll try to see if I can understand this from the boundary point of view. So from the book point of view, like basically you see that this shifts the energy, and it's either positive or negative depending on the sign of H. But as I think you asked an interesting question in the sense that if there is some coupling, this should generically allows you to send the information through the wormhole. So I don't think I have a good answer for this. Like this is the same type of feature that appears in Gauss-Jeffreys and Wall setup. But unfortunately, I don't think I have a good understanding of this, but that's a very good question, I think.
Maybe I can ask a similar question, like this neural energy condition that you have to calculate for this shock. That because you need some negative the condition for this neural energy condition. So that one, is it proportional to the H square or H here?
It's proportional to H actually.
H.
Yeah. Yeah, so I don't know, like maybe the double trace deformation acting on both sides is somewhat artificial, but yeah, I don't think I have a good understanding of this from the boundary point of view.
But anyway, thank you for your interesting talk.
Yeah, thank you for the interesting questions. Like
I enjoyed.
I'm sorry I was not able to give like a proper, very good answers, but I will try to come up with some better answers, like for you in the future, like in future discussions. Like.
Okay, so I think it's a good moment to thank Viktor again for the talk.